Yes.
And our speaker is Damian Frölich.
Yes, thank you for the introduction. So I'm Damian Frölich. I'm a PhD student on from the University of Amsterdam, and I'll present the work on soundness of autocompletion services for dynamically typed languages. So the modern day programmer is supported by a variety of services. Think of syntax highlighting, debugging, refactoring, go-to definition, etc. Another service is the autocompletion service. From a very high level, it's a pretty easy service. Here we have three components. We have a user, we have a client, which is a text editor or an IDE, and we have a language server, which builds a model of the language and responds to queries from the client. So the user performs a typing action, the client sends a completion request, the language server responds with a list of completions, and then the client shows a completion picker to the user, and the user can pick a completion or ignore it. This speeds up coding maybe a little bit, but a nicer thing is that it helps with discoverability. Think, for example, when you're programming in an object-oriented language, you access an object and all the fields and methods are shown in the completion picker. And building a completion service is pretty simple, right? We can just collect all variables in the program and present those as completion candidates, and we are done. Well, we get many unrelated completions then, and this is mentioned as one of the main complaints from programmers when they use completion services. And one of the anonymous reviewers put it very nicely, I think. The only correct completion candidate is the candidate picked by the user. So in an ideal world, the completion service would give one completion candidate, and that is the one that's actually picked by the user. Now, this might be an ideal that is not achievable, but between only giving all variables in the program and only the one that is picked by the user, there are a lot of different choices with regards to design. So here we have a little example, a Python program. So throughout this presentation, all the examples will be in a Python-like language. We have two classes, class A and class B. They both have a field X, and class A has a field Z, and class B has a field Y. Then our program is pretty simple. We instantiate an object variable as an object of class A. We assign some dynamic input to the X field, and based on that input, we either change the object variable to an object of class B, or we do nothing. And now, here, this represents our cursor, and at this point, a completion request is sent to the completion candidate. Now, the question is, at this point, what are the valid completion candidates? Anybody a suggestion what the valid completion candidates can be in this program? So XYZ is indeed a very good suggestion, since it is a union of the fields on both classes, and this is also what most programming editors do. They give X, Y, and Z. However, Y and Z can introduce erroneous program flows, because their presence is dependent on whether this if condition is true or not. And in this little program, this is easy to see, but when you're working in a bigger project, it can be difficult to keep track of all different fields that are present on all different objects. So a sound completion candidate would only be X, because that's the only field that is present on both objects. And that raised the question, or that brought us to the question, can we implement an autocompletion service that only gives sound completion candidates, so that the user, when they pick a suggestion, that they are sure that it does not introduce any bugs at runtime? Now, what actually is a sound completion candidate? Throughout our research, we found three types of soundness. One is syntactic soundness, where a completion candidate can give terms of the language as completion candidates. So for example, this is our little program. At the question mark is again where a cursor is, and that is where a completion request is sent. And with syntactic completion, it could, for example, complete into another plus expression with two holes, which can then be filled in by the user. Syntactic soundness would then be that these suggestions actually follow the grammar of the language. With name soundness, these suggestions do not introduce any errors with regards to name binding. So in this example, X and Y are valid because they are in scope, but Z is not valid because Z is being defined and not in scope. If you would try this example in any editor, they will give X, Y, and Z as completion candidates. A stronger type of soundness is type soundness, where the completion candidates not only introduce no name binding errors, but also no typing errors. And in that case, only Y is a valid completion candidate, because X is a type string, and that would cause a typing error. In our work, we focus on name soundness, and in the future, hopefully on type soundness. So our contribution from a very high level point of view is pretty simple. We take in a program, we perform abstract interpretation, we get a model of the name binding seen at runtime, and using that model, we generate sound autocompletion candidates. So what is abstract interpretation? It is a static analysis framework which does a interpretation of a program in an abstract domain. The advantage of this is that we can analyze non-terminating programs in this abstract domain, and in the abstract domain they terminate. So here we have a little example where we have integers. We abstract this by the signs. So operations on integers become operations on signs in our abstract domain. So 2 plus 2 becomes positive plus positive, which is a positive number, while 2 plus minus 2 becomes positive plus negative. And we don't know the sign of that. We don't know whether it's positive or negative, so it becomes just a num. And with this information, you can analyze a program and, for example, determine that certain if conditions are always true and optimize them out, for example. There are many more options you can do with abstract interpretation. Our name binding model is based on scope graphs, which are a abstraction for name binding, and there are 3 main components. So it builds a graph where we have vertices of different types. We have scopes, which are here the nodes with a number in them. We have declarations, which are here with the rectangle. And a scope has an edge towards the declaration, which means that that declaration is defined in that scope. And we also have references which go into a scope, and that means that that reference is referenced in that scope. And throughout this example, you see these little subscripts on variables that denotes a program location. So all the x's here are the same variable, but they are at different program locations. And now what we can do is we can find paths in this scope graph to determine to which reference a declaration resolves. So for example here, we have a reference to x. We can take a path to 2. There are no x's here for declarations. So we take a parent edge to scope 1, and we see that this reference of x resolves to this declaration. So that is what we use to build our name binding. And later work, they introduced a scope described frames model where scopes essentially function as a blueprint for the heaps you see at runtime. And this is nice because it can be used, for example, to implement sound garbage collection algorithms. In our work, we use the one-to-one correspondence between scopes and frames the other way. So we use frames and heaps to build scope graphs. So now that we know a bit more, our approach is a bit less simple than shown earlier. So we take a program, we do abstract interpretation, and out of that we get for every program point all the heaps seen at runtime, and then we collapse that set of heaps into a scope graph. So now what we get is we get for every program point, we get a scope graph. And with that we can do an analysis. Now, how do we actually get this? So in our framework, the language semantics has to be defined in an operational style with explicit frames and heaps, which is a bit unfortunate. So here you see 2 language constructs and their semantics. One is subtraction and one is a function call. Most of this stuff you can simply ignore. The main thing I want you to focus on is that we explicitly track these heaps through our evaluation. And what you can see is that even expressions modify the heap. This is because we also track references. And an expression can reference a variable, and that is then added to the heap in our approach. Secondly, we use frames to construct scope graphs, but scope graphs have a unique ID, so we somehow need to keep track of that. And for that, we have this init frame function, which takes a location. And in this case, we keep the location, the source location, we keep those in our closures and then pass those to the init frame. So essentially, how you can understand this is that every frame has an associated identifier, and that is simply the source location of the function that was called. So after defining your language operations with the semantics, we can generate all the autocompletion stuff from this definition. So that is nice. So what we can do is we can define a collecting semantics, which is simply just all the heaps seen before a program evaluation and after a program evaluation. So that is what we say here. So let's see a little example. Here we have a little Python program. We assign a variable x to something. It doesn't really matter what. And based on that value, we either introduce a variable y or we introduce a variable z. Now the problem with dynamic languages, well, not all, but in this case Python, is that after we go out of this if and else condition, these variables introduced in these branches are available to us at the end of the program. That is something that we need to keep in mind. So what we do is we evaluate this into a set of all seen heaps. So at the end of the program, we have seen two heaps where we have a frame 0 where x points to an integer. So we use integers, that's our abstract domain. So no values, but instead the type of the value. And we have a frame 1, which is y points to an integer. So that is the frame that corresponds to the evaluation where the condition was true. Then we have another frame where we now have a frame 2 of another heap where we have a frame 2 where set points to an integer. And that corresponds to the evaluation where the if condition was false. Then we collapse this into a scope graph, which we see here, and this scope graph then represents the information of all the heaps seen. So what we have here is we have a global scope, then we have an import edge to scope 1, because at the end of the program, the variables introduced in these branches of the if-else are still available to us. So we have to somehow be able to reach these declarations, y and z, from our global scope. Hence the import edge to the corresponding scopes. So now you might see, what did we get? Well, we got absolutely nothing, because when we walk this scope graph and find all declarations visible from scope 0, we can take a declaration edge to x, and we can take our import edge to S2 and then get z and also y. So now reachable declarations from S0 are still x, y, and z. But in the introduction, we saw that only x is a sound completion candidate, because y and z are not always in scope. It depends on the execution. So all that work, and what did we get? Absolutely nothing. So to solve that, we introduce annotated over-approximating scope graphs. So at runtime, we actually see two scope graphs corresponding to our two heaps. So one where we have our scope S1 and one where we have our scope S2. We then merge these two together with annotations on the declaration and references and annotations on the edges. So blue means that a certain node is definitely in scope, and red means that it might be in scope, but it might not be in scope. And these annotations are from a scoping perspective. So if we look from scope 0, we can see that our import edge is red. So that import edge might be present, but it might not be present. And as a result, when we traverse this path, we reach y, but there is a red edge on that path. So that means from the scope S0, y is also maybe in scope. However, from the scope S1, y is definitely in scope. So it's from a scoping perspective, we can see that our name binding behaves differently, or the available declarations are differently present. So now the situation we have is we have these annotated scope graphs, we can query them and obtain these completions that are sound, because what we do is we only query the definitely present values. So if we now query from S0 the available declarations, we would only get x, because that is the only one that is definitely in scope. And that means that we get sound completion candidates. So now we have these scope graphs at every program point. However, most statements have a very simple and monotonic effect on our scope graphs. So we can reuse some stuff. So this is our current situation. We have a scope graph per program point, a lot of duplication, which is not ideal. The ideal situation would be one scope graph where we can perform all queries on. This also is nice when, for example, a user changes something in the program. We don't have to reinterpret the whole program. We can maybe do some modifications on that single scope graph. However, reality is somewhere in between, where most statements have a monotonic effect, but not all. Think, for example, here the y might do a function call, and the function call changes the fields on an object by, for example, removing a field. So that is not a monotonic effect. So we need to keep some around, but sometimes we can collapse multiple scope graphs together. The only problem we then get is that our queries are not sound anymore. Because let's take the ideal scenario where we have just one scope graph. For scope graph G3, x and y are in scope. But if we use this scope graph at the point of G1, where x and y are not in scope, we would get the wrong results for our queries. So to solve that, we introduce context-dependent name resolution, which essentially means that we keep track of the context from where the query is performed. So essentially the current cursor location. So these are the rules for the resolution calculus to determine a reference to a declaration. And most of this you can ignore. The main thing are these gray boxes, which are added. So here we start from a reference, we keep track of the current source location. And then when we reach a declaration, we check whether the declaration was introduced before our current source location. So this way we can reuse collapse multiple scope graph into one, while still allowing our queries to be sound with respect to the name binding. So to obtain auto-completion candidates now, it's actually pretty simple. We simply query all the definitely present declarations from a specific scope for a possible program point. That's all. That's how we get all the completion candidates at a specific point. Now, how well does it work? To determine that, we implemented our approach on a subset of Python and compared the completions that we gave to the state of the art. So we compared it to Pylons, which is the VS Code implementation used in, of the Microsoft implementation used in VS Code, Jedi, which you can also use in VS Code, and PyCharm, which is the JetBrains IDE. And these are our results. I will go in depth on several programs. The main thing I want to highlight here is that we report the results in a precision recall pair. A sound approach would have 100% precision, and a complete approach would have 100% recall. Now, it doesn't mean that if some approach is 100% sound, of 100% precision, it's sound, but it gives an idea. Secondly, the values here are the sound completion candidates and the possible completion candidates. So what we did is we executed the programs trying to achieve 100% part coverage, and then taking the union of all the variables available across all paths, and that determines our p plus n, and then the intersection is essentially our p. So let's look at some example programs. This is a simple example where the if condition is always false. So this branch is never taken, and at the end, both x and x3 are in scope. And this is handled nicely by Jedi. PyCharm and Pylons, they give all three of the variables as completion candidates, and our approach only gives the first one as a completion candidate. And that is due to the abstract domain we use, which are types which do not track these values. So in our evaluation, this x would just be an int and not the value 0. We can adapt that by using a more complex abstract domain. Here we have a more complex program where it really shows the dynamic nature of name binding in Python. So we can have two classes. We have a simple function which takes in an object and then does an access on that object on a field x. And then at this cursor, we do a completion. Now, the rest of our program creates two objects, one of class A, one of class B, and then calls this function with our object of class A and object of class B. So the available completions in this function are dependent on the arguments passed to the function calls. So in this case, both O can be an object of class A and an object of class B. So again, the intersection of the fields is the sound completion candidates. And this is handled well by our approach and not by PyCharm and Jedi, while Pylons give no completion candidates, hence the not acknowledged. Now, if we would, for example, remove the second call, then only A would be passed as a parameter, and then the sound completion candidates would change to simply the fields of A. So depending on the evaluation of the program, the available completion candidates can change in a function. Here we have another example where we have a function that introduces a global variable, and then we call this function and we do a completion on it. So after this call to this function, we have both x and x6 in scope. Now this is handled well by Jedi and by our approach, also by Pylons. PyCharm does not complete on the global, it simply completes on x. Now if we remove this call to add global, then our global is never introduced, so it's not a sound completion candidate. That is the second case, which is handled well by PyCharm because they simply do not complete on globals. But it isn't handled well by Jedi and Pylons, but it is handled well by our approach. So then are we perfect? No, we are definitely not perfect because, for example, when a function is not called, it's not processed by our interpreter. So for that, we don't give any completion candidates, which is kind of unfortunate. And this little example is handled perfectly by all the other services. So the next steps, we want to turn this evaluation into a micro benchmark for soundness of auto-completion services, and then also look at type soundness. Do an analysis of our programs in a more incremental manner where changes to a program do not require a full re-evaluation of the full program, which is very important with auto-completions. More case studies, so we're working currently on a Lua implementation of this approach. And I showed you earlier these operational rules which have a lot of baggage with these heaps and these frames that you have to track. We want to automatically derive such interpreters from regular operational semantics, having to do less, so that's nice. Also, it's not always nice to not get unsound completion candidates. Think, for example, when you're refactoring or maybe doing some kind of prototyping, then you might know that certain completion candidates are unsound, but you still want to pick them. So what we want to do is include this soundness information on the client. So for example, annotate certain completion candidates with, hey, this might be unsound, be aware. And also experiment with different abstract domains. So I showed where we didn't take into account the 0 value of our if statement. More complex abstract domains might do that well. And also handle invalid programs, which we currently do not do. So to summarize, we apply abstract interpretation to build a complex, model of the name resolution seen by a program, and to achieve this and get auto-completion candidates based on that model. To achieve that, we used scope graphs, which we extended with annotations and context-dependent name resolution. Thank you for your attention.
All right. Who has questions?
Really quick one. Could you just explain what precision and recall mean again?
Yes, of course. So precision means how many of the given completion candidates were actually sound. So in that case, it checks how many of this P plus N was actually P. And recall means how many of the given sound completion candidates were actually given. So how many of these P's were actually given.
All right, thank you.
Yes, thank you for the talk. One thing that is puzzling me a bit, how's your work related to intersection types? So I'm pretty sure internally you are computing them, but I'm not sure, are you doing more than that? Maybe the question is a little bit mean when you haven't thought about that beforehand, but I couldn't grasp that, therefore I'm asking.
No, it's a good question. I do think that there might be a type-based approach that can solve most of these things. I think a primary difficulty is that for autocompletion in dynamically typed languages, you need some kind of data flow analysis. And the goal of this approach is to essentially do both at once. So kind of this intersection type ID and this data flow analysis kind of ID. But I think I must also be. I think in certain situations this approach requires too much compute. So it would be nice to extend the existing approaches, which, for example, Pylance does a type-based approach, a type inference-based approach. But based on the experiments I performed, it seems pretty simple. So maybe extending that with intersection types would be a nice middle ground to achieve good results with little compute. Thank you for your question.
Okay, who else has a question?
I have another one. Have you seen the stat graphs coming out of work at GitHub? Do you think maybe there's anything you could do with that, or anything you'd be interested in extending this by maybe making use of those, or some, I don't know, similar ideas?
Yes, I did see the stack graph approach. I found it very interesting. I didn't find that much information on it, unfortunately, but I saw one presentation, and I think they also use data flow analysis in their approach to handle complex situations. So I think it's a very nice approach, and this might be just a different take on the same difficulty of the same ID. But I think they are also mostly used for code navigation. So I'm not sure how well they would perform for autocompletion, but it would be interesting to experiment with that.
Oh, thank you.
Thank you.
Yes.
Thank you for the talk. So I was wondering, you discussed a little bit at the end that you could extend the results with soundness information, right, to also show unsound possibilities. What happens if you do a path-sensitive analysis where you actually know under which conditions a name is valid? Then you could propose something like, oh yeah, you can refer to Y, but only if you also wrap the current expression in a condition that matches the condition under which Y was defined in the first place. I mean, I think it's kind of interesting that you have this abstract interpretation approach, right? And there's a lot of work on how to make that more precise. Why not exploit that?
That's a very good point. I haven't thought about that, but one of the reviewers did give a example program that kind of showed that we currently don't do. But yeah, it's a very good point. We just haven't implemented it yet, but it sounds very interesting, and I think it would definitely be possible with the approach.
Anyone else? So I was wondering about the context-dependent name resolution that you quickly went past. Because this was part of combining scope graphs at different points in time in the program, right?
Yeah.
So I was wondering, can't you express that in the shape of the scope graph anyways? Where you have, if you have a sequence of statements, those are different scopes?
Yes, I have thought about that, because this is one scope graph for this program, but we could come up with a different scope graph that kind of encodes the same thing. But the difficulty I encountered when trying that was that at this point, at the end of the program, we still need access to these points. So we need some kind of way to link our global scope back to these things. And there might be a way to encode that information in some kind of different scope graph, where you might duplicate some information that is present here in a new scope, and then you have a better way to track that. That might be a valid way to solve that. I haven't tried it out yet, but it might definitely be possible. Yes.
All right. Any last question? If not, then let's speak. Thanks, speaker.